So the next step in this test is to compute the deviation from expected. 4 minus 5 is a negative 1. 6 minus 5 is a positive 1. So this number here is 1 less than what we expect if the distribution is in fact normal. This observed frequency is 1 more than what we expect if in fact the distribution of the error is normal, etc., etc. Notice for the fifth interval, the observed frequency is 9. This is 4 bigger than the expected frequency of 5. So we continue this for all remaining intervals. In this interval here, we observe 5 residuals between these two numbers, which is exactly what we expected. Now the final step is to square this difference and then divide by 5. So minus 1 squared is 1. 1 divided by 5 is 0.2. 1 squared divided by 5 is 0.2. So all these values are 0.2. Now 4 squared is 16. 16 divided by 5 is 3.2. 2 squared is 4. 4 divided by 5 is 0.8. 0 squared divided by 5 is 0. Yada yada yada. I think you get the point. Now here are the rest of the observed frequencies. This is the 20th interval. And notice in the 20th interval we had 5 residuals between these two numbers, which is exactly what we expected. And that's why the deviation from expected is 0 here, and the square deviation from expected divided by expected is 0 here as well. Now the chi-square stat adds up all 20 of these numbers, and when you do that you get a number equal to 11.6. Recall that the chi-square distribution is skewed to the right, and the distribution covers all positive values from 0 to positive infinity. The expected value of the chi-square distribution is equal to the degrees of freedom, 17. Since the alpha is 0.05, we shade the upper tail probability 0.05. This is an upper tail test because we want to know if the difference between the observed frequencies are quote-unquote close to the expected frequencies. The closer the expected frequencies are to the observed frequencies, the closer the chi-square stat will be to 0. For the most part, the observed frequencies hover really close to the expected frequency of 5. The chi-square stat should be really close to 0. Now, as the observed frequencies deviation from expected gets larger and larger and larger, the chi-square stat gets larger and larger and larger, and we have less and less evidence to support the hypothesis that the errors are normally distributed. The chi-square critical value is found in column 0.05 and row 17 of the chi-square table. When you go to row 17 in column 0.05 of the chi-square table, you'll find 27.587. The critical value defines the do not reject the null and reject the null hypothesis regions. If the chi-square stat is in the do not reject the null region, the errors are probably normally distributed. If the chi-square stat is in the reject the null region, then the errors are probably not normally distributed. Our chi-square stat is equal to 11.6, well within the do not reject the null region. Hence, there is no reason to doubt the assumption that the errors are normally distributed. If the errors are normally distributed, parameter estimates are normally distributed. F and T tests are valid. If the errors are not normally distributed, but the sample size is large, parameter estimates are approximately normally distributed by the central limit theorem. F and T tests are valid. If the errors are not normally distributed and the sample size is small, parameter estimates are not normally distributed. F and T tests are not reliable. In this class, what constitutes large and small is beyond the scope of the course. The fourth assumption that has to be verified is that the values of the error are independent. Now, the values of the error are probably independent if the autocorrelation residual plot or the Durbin-Watson statistic indicate the values of the residual or estimated errors are independent. No autocorrelation is present if DW stat or the Durbin-Watson statistic is equal to 2. Perfect negative autocorrelation is present if the Durbin-Watson statistic is equal to 4. Perfect positive autocorrelation is present if Durbin-Watson statistic is equal to 0. What we want to see is the Durbin-Watson statistic near 2. How near 2? Well, that's beyond the scope of this introductory course. The Durbin-Watson stat varies when the data is ordered. If you have cross-sectional data, you really don't have to worry about computing Durbin-Watson statistic in most instances. If you have time series data, compute the Durbin-Watson stat after sorting by time. If you have panel data, compute the Durbin-Watson statistic after sorting by state and time. To compute the Durbin-Watson statistics for the R data, we start by computing the numbers in this column. Now, since we don't have a previous year for Alabama, we can't compute the difference between this residual and the previous year's residual. So that's why we have a dash here. However, we can compute the squared difference of these two residuals because in the year 2000 there is a previous value for the state of Alabama. So to compute this number here, we take minus 4.110, Alabama's 2000 residual, and subtract from it 8.522, Alabama's 1994 residual. When we square that difference, we get 159.57. Now again, we can't compute a number here because we don't have a previous residual for Alaska. So we just put a dash right there. In the year 2000, we have a previous residual for Alaska. So we take this difference and square it. When we do that, we get 293.25. We continue doing this for all the rest of the states. Next, we want to sum this column. We sum this column and we get 2,889. This is going to be the numerator of the Durbin-Watson statistic. The denominator of the Durbin-Watson statistic is found by squaring all the residuals. 8.522 is equal to 72.63. Negative 4.110 squared is 16.89. Negative 2.290 squared is equal to 5.24. 14.835 squared is 220.08. We do that for the rest of the observations. Next, we sum this final column, and we get 3,747. The Durbin-Watson statistic is therefore equal to 2889 divided by 3747, which is 0.77. So the errors may not be independent. If autocorrelation, also known as serial correlation, is a problem, estimated coefficients aren't biased, but their standard errors may be inflated. An inflated standard error reduces the value of the t-stat. So you're more likely to make a type 2 error, meaning you may end up rejecting a true alternative hypothesis. So you conclude that a slope is equal to 0 when it really isn't. Hence, hypothesis testing is unreliable in the presence of autocorrelation. In our example, autocorrelation seems to be a problem. If autocorrelation is a problem, do one of the following. Change the form, include a no-motive variable, use generalized least squares, compute new West standard errors for the estimated coefficients. All of these corrections are beyond the scope of the course. The final assumption to verify is that the true model is linear. Now, the true model is probably linear if the scatter plot of the residuals, the estimated errors, versus y hat, the predicted values of the employment population ratio, is a horizontal random band of points. Now I constructed this scatter plot in Excel. Excel allows you to right-click on one of these points to insert a trend line. Now the trend line I inserted was actually a graph of a quadratic equation. The equation for this curve here, which looks like a flat line, was spit out by Excel. Had this red curve been really bowed this way or really bowed this way, we would have had evidence that would not support the hypothesis that the true model is linear. However, because the curve of this quadratic equation is rather flat, the data suggests that the true model is probably linear. If you fit a linear model to data which are non-linearly related, estimated coefficients are biased. Predictions are likely to be seriously in error. If the estimated coefficient is biased upwards, the t-stat is going to be biased upwards. If the estimated coefficient is biased towards 0, the t-stat is going to be deflated. In our example, nonlinearity does not seem to be a problem. If the data are nonlinearly related, do one of the following. Rethink the functional form, transform one or more of the variables, like for example we transformed the dollar value of the TANF benefit for a family of 3 into logged dollar values. 4 of the error assumptions appear to be valid. Only the autocorrelation assumption appears to be invalid. Hence, the T and F tests are going to be unreliable. For instructional purposes, we're going to assume that all 5 of our tests involving the error assumptions were valid. If all 5 are valid, then we proceed to hypothesis testing. And the first test we want to conduct is a test for overall significance. In simple linear regression, the F and T tests provide the same conclusion. Because remember, there's only one independent variable in simple regression. So the t-stat was equal to the square root of the f-stat. As a result, the p-value of the t-stat equals the p-value of the f-stat. In multiple regression, there are many independent variables in the equation. So the F and T tests have different purposes in multiple regression analysis. The F test is used to determine whether a significant relationship exists between the dependent variables and the set of all independent variables. It is referred to as a test of overall significance. The null hypothesis is all slope coefficients are equal to 0 simultaneously. The alternative hypothesis is at least one parameter is not equal to 0. The test statistic in either simple regression or multiple regression equal to the mean square due to regression divided by the mean square due to error. We reject the null if the f-stat is larger than the f-critical value. The f-critical value is in column degrees of freedom for the mean square due to error, and row degrees of freedom corresponding to the mean square due to error and the alpha level. The equation at the top is the predicted multiple regression equation. The number below it is the sample mean y bar. Now we already predicted the y-hats. All we did is we plugged in the first observed value of natural log x1. We plugged in the first value of x2, the first value of x3, the first value of x4, the first value of x5, and the first value of x6, and we got 43.83. Now to compute the first squared deviation in y from its sample mean, we take the observed value of y and we subtract off the sample mean, and we get 4.47 when we square that difference. The first squared deviation from the observed value of y and its predicted value is found by taking this difference and squaring it, and we get 72.63. The value in this last column is found by taking the predicted value and subtracting off the sample mean. And when you square that difference, you get 41.05.